Question number 11. A force F acts on a body and the body moves a distance d in the direction of the force. So let's say we have a body like this. It has some mass m and a force is applied on the body which is F and the body moves a distance which is d. So after some time after the force is applied, the body is over here. Okay. Which expression for work done W is correct? This is a direct formula. You have to remember this, which is W work done or energy, we also call it energy, is equal to F multiplied by D. So W is equal to F multiplied by D. Checking the options, option A is correct. Question 12. We have a boy who produces an average power output of 60 watts as he rides his bicycle. So power is equal to 60 watts, P equals 60 watts, and he rides his bicycle for 2 minutes. So time, which is small t, is equal to 2 minutes, which is also equal to 120 seconds. Now, how much useful power does he expend? Okay, we know that the formula for energy E is equal to power multiplied by time. So we can directly plug in values into the formula. So 60 watts multiplied by 120 seconds, which will be equal to 7,200 joules. Checking the options, the answer is D. Question number 13. So this is a purely conceptual question. We have been given a diagram. This over here is some kind of tumbler and it has been filled with water. And there's a stone that is raised down inside the water using a string. This over here is a string. The question is, what would increase the pressure on the stone? Let's think about what is happening here. Now, this water over here, there's a water column above this stone that looks something like this. This may be a cylinder, it is exactly above the stone. That water over there has a mass, and because it has a mass, it is being affected by gravity. It is applying a force which is equal to mg. And because it is applying a force, it is also applying a pressure which is equal to F over A. So there's a pressure on the stone due to the water. Now let's think about the options. We have to tell which option would increase the pressure on the stone. Option A says decreasing the surface area of the stone. Let's think about what happens when we decrease the surface area. As we will decrease the surface area, the total water column on the stone will be reduced. The volume of water over the stone will reduce. Maybe it will become this much as the stone's surface area is decreased. As that is decreased, the total pressure will remain the same because F will decrease and also A will decrease. So this is wrong because the pressure will remain the same. Option B says increasing the mass of the stone. Well, for pressure, we actually care about the mass of the liquid above the stone and not the actual mass of the stone. We don't care about the mass of the stone, so this is wrong. Option C says lowering the stone deeper into the liquid. This seems like the best option because if I lower the stone deeper into the liquid, the diagram looks something like this. Maybe the stone is over here and this is the water level. Now you can see that the height of the water column has increased. Because the height of the water column has increased, the mass of water over here, m, is greater than this mass. Because the mass is greater, the force will also be greater. And the area will yet remain the same. Force divided by area, this force over here applied by the water column is increased and therefore the pressure will increase. Seems like we have got our correct option, but let's look at option D too. Option D says using a liquid with a lower density. If we use a liquid with a lower density, that will mean that the mass of this water column decreases. As this mass of this water column decreases, the pressure will also decrease. So this is exactly opposite of what we need. So D is also wrong. Seems like C is our correct option. Question number 14. This is again a conceptual question. At room temperature, iron is difficult to compress. At the same temperature, oxygen is much easier to compress. What comparison of structure of iron and oxygen explains this? Okay, let's think about the structure then. We have been directly indicated in the question that we have to think about the structure. Let's think about the structure of oxygen atoms, oxygen molecules at room temperature. So the molecules will be quite scattered and they will be quite far apart. Because they're far apart, that means that if we compress this, it may become something like this. So let's say I compress it into a smaller space. So the molecules will be closer together. I think that's the only difference that will happen once we compress it. Now let's think about what will happen to iron. The molecules over here are very close already. They are packed completely at room temperature. So they're very close. If I try to compress this iron, if I apply a lot of force, the iron will not be compressed so easily. It will still remain packed, and if I apply a lot of pressure, maybe it is compressed a little bit. But it is very difficult to compress this iron because the molecules are already so close together. That is the reason why it is so difficult, because the molecules are already so close together. Let's look at the options. Option A says the iron particles are close together. Well, I think we have found our correct option. Let's just star it and think about the rest of the option. Option B says the iron particles have a greater mass. This is true, but it is irrelevant to us. We don't care about the mass. We are talking about compression, not how much force they exert on Earth or on the surface they are on. We don't care about the mass. So option B is wrong. Option C says the iron particles can be magnetized. We don't care about magnetism. We are talking about compression. Magnetism doesn't come into play. So C is wrong. Option D says the iron particles have less average kinetic energy. Now, this again is true, but we don't care about it because kinetic energy does not have relation to compression. The thing we care about is atoms being close together and being difficult to compress. So D is also wrong. Like A is our answer. Question 15, again a very conceptual question, says we have a block of some material, and it is heated during the night, and during the day it basically cools off. So the energy it has stored, it releases it and therefore heats the room. Now we have to tell which thermal capacity and what nighttime temperature will increase the most energy to be stored by the block. Now let's think what thermal capacity really is. What does it mean? Thermal capacity, as you can read the definition, is basically the amount of energy required to raise the temperature of a substance by 1 degree Celsius. So, like if the thermal capacity of a material per gram is maybe 100 joules, 100 joules, I'm sorry for the degree, 100 joules, that means that I will need 100 joules to raise its temperature for 20 degrees Celsius to 21 degrees Celsius. Now, this also works in the opposite way. It basically means that if a material, 1 gram of a material, is at 21 degrees Celsius, it will release 100 joules when it goes down to 20 degrees Celsius. That can tell you that if we have a higher specific heat material, if I have 1 kg of a material that has a specific heat of 1000 joules compared to 1 kg of material which has a specific heat of maybe 90 joules, that definitely means that this material will store more energy than this one. And this is actually used. Water has a high specific heat capacity, therefore sometimes we might use it to store energy. So we need a higher specific heat capacity to store more amount of energy per degree Celsius. So options C and D are immediately eliminated because they talk about smaller specific heat capacity. Now, nighttime temperature increase. We want to know if we should have a higher temperature or a medium temp or a smaller temperature at the night. Okay, so when we were talking about specific heat or thermal capacity, we talked about the higher thermal capacity we have, it will be per degree. So, using a similar argument, we can see that if I have a block at 80 degrees Celsius versus if I have a block at 40 degrees Celsius, this block will cool down to room temperature. Let's say the room temperature is 20 degrees Celsius. It will cool down to 20 degrees Celsius and the change in temperature will be 60 degrees Celsius. While when this cools down, it will change, the change will be 20 degrees Celsius. Now we can immediately see that when we have a change of 60 degrees Celsius, it will release more energy. It will release more energy, actually 1000 joules per degree Celsius. So this one will basically emit 60,000 joules of energy, whereas this one will just emit 20,000 joules of energy. So we can just directly see using an example that this option over here is better. So the higher the temperature we have, the better. Therefore, A is our correct option because it says large for both of them. B is again wrong because it talks about nighttime temperature increase being small. Question number 16. This time we have a purely mathematical question. Let's go through it together. Question 16. 100 grams of water at 25 degrees Celsius is put into an insulated cup. The part about insulated cup just means that there is no heat loss into the surroundings. So 100 grams of water at 25 degrees Celsius. 50 grams of ice at 0 degrees Celsius is added to the water. So 50 grams of ice, which is basically frozen water, at 0 degrees Celsius is added. So the cup contains all of these. Now the water is stirred until the temperature of water has fallen to 0 degrees Celsius. So water goes from this to 100 grams of H2O, but this time at 0 degrees Celsius, and ice goes from 50 grams of ice at 0 degrees Celsius to 32 grams of H2O at 0 degrees Celsius because that part has melted, and 18 grams of ice at 0 degrees Celsius. So now let's think about what changed. What happened was water provided heat to the ice. Water cooled itself down, providing heat to the ice, and ice got heated up. So 32 grams of ice got heated up and got converted to H2O, while water provided heat as it cooled down. The specific heat capacity of water is 4.2 joules per gram per degree Celsius. If we want to know how much heat water provided, let's say it's H, it will be equal to 100 grams multiplied by the change in temperature. So 25 minus 0, delta T is 25 degrees multiplied by 25 degrees Celsius multiplied by the specific heat capacity of water, which is 4.2 joules per gram degree Celsius. We can see that the units cancel and we get joules over here, which means that we are performing the calculation correctly. This is equal to 10500 joules. So 10,500 joules of energy is released by the water. So this is the amount of energy that ice gained. Now ice, 32 grams of ice got converted from ice to H2O to 32 grams of H2O, both at 0 degrees Celsius. So this means that there was only a change in state. That means we are talking about the latent heat. Let's see now. We were provided with 10,500 joules, and that was divided equally into 32 grams. So the latent heat of ice, of fusion, from ice getting converted to water, so I'll write ice to H2O, which is liquid water, is equal to 10,500, which was the total heat that was provided by water, divided by 32 grams. So joules divided by grams, because this was provided equally to each of 32 grams. 328.125 joules per gram. Checking the options, this is almost approximately equal to 330 joules per gram. Therefore, option B is our answer. Question 17. This is again a conceptual question. The handle of a metal saucepan is made of plastic. As the saucepan heats up, the handle gets warmer. Which statement explains this? Okay, so we have a piece of plastic that covers a saucepan. So the center part over here, I'm very sorry for the bad drawing. The center part over here is the saucepan's metal. So this maybe is the saucepan over here. This is made of metal, and this handle over here, the block, is plastic covering. And we have to tell which statement explains the plastic covering getting warmer as we provide heat to the saucepan. Let's think about what, first of all, heat transfer using conduction is. Basically, what happens is if we have two atoms side by side, these are the two atoms. This atom over here jiggles. The more it jiggles, it means that the more heat it has. As it jiggles, it rubs the other atom, and the other atom starts jiggling. The atom to the right side of this atom will also start jiggling, and maybe another atom over here will also start jiggling. This Through this process, it will continue to provide heat to transfer heat to its surrounding. That is how conduction takes place. Let's now look at the options. A. Molecules of plastic radiate their energy to the other molecules. No, we are talking about solids, so conduction is our only option. Therefore, A is wrong. Radiation is not true. B. Molecules of plastic vibrate more and more and pass on their energy to nearby molecules. This is correct because this is what I explained. A molecule over here will jiggle, will vibrate, and it will make this one vibrate, it will make the other one vibrate, and therefore the energy passes on. Therefore, B seems like a very promising option. Let's see option C. The free electrons in the plastic transfer the thermal energy along the handle. This is wrong. There are no free electrons in plastic, they are in metals. This is a conduction process that happens in metals, so this is wrong. Now, D says the heated molecules very slowly move along the plastic handle. This again is wrong. Plastic is a solid and molecules are fixed in their place. They cannot move along. So this is also wrong. Seems like we have got our answer, which is B. Question number 17. We have a kettle which is hot. The surface of the kettle is hot. And we have to tell what happens to the cool air outside the kettle when it comes in contact. So we have air around here. Obviously, air is in the surroundings and it is colder than the surface of the hot kettle. Let's think about what happens as the air comes in contact with the metal surface. Because the metal surface is warm, as soon as air molecules will come in contact with the surface, they will become warmer, they will have more energy. That means the air will become warmer. Now, so the temperature of air increases. As temperature increases, we know that the molecules will start to jiggle more, their speed will increase, their kinetic energy will increase, and therefore they push each other apart. And so the density of air becomes less. And we know for sure that hot things rise. So, as the temperature rises, the air will become hotter and it will try to rise. So, the air over here in this section will try to rise up. It will go up compared to the air that is over here. It will always rise up. Hotter fluids rise from colder fluids. Another explanation for why they will rise is that their density is lower than it was previously. Lower density fluids rise always. You can remember this. So they will rise. Let's see the options now. A says the density of air decreases and air falls. Now, the density part is correct, but air will not fall. So, this option over here is wrong. Option B says the density of air decreases and the air rises. Okay, density decreases and air rises. This is absolutely correct. That is what we talked about. Density decreases and air rises. So B should be correct. Let's see option C. The density of air increases and air falls. This is again wrong because the density actually decreases. Option D. The density of the air increases and air rises. Again wrong because density actually decreases. So we have found our correct option, which is option B. Question number 19. We are talking about vacuum flasks. So I have drawn a vacuum flask over here. This is a kind of a bottle, and what happens in vacuum flasks is for every wall we have kind of two walls. In between these walls there is a vacuum. This is the between section, and over here the walls are silver colored. So basically they are shiny, and we are asked why are the walls silvered. For this question we can directly go through the options. So option A says to absorb thermal energy from the air around the flask. We cannot absorb thermal energy from around the flask. The contents inside the flask will already be at, let's say, 50 degrees Celsius. The air outside will be at room temperature, which maybe is 25 degrees Celsius. So there is no way we are absorbing heat from the air. In fact, heat will try to escape outside because heat will try to go to a place of lower concentration of heat. So A is wrong. B says to increase the rate of convection inside the flask. This is not correct. Silvered walls will not make a difference to the rate of convection inside the flask. That will happen only if the temperature inside the flask is higher or if the flask is heated. So this is wrong. Silvered walls will not make an effect in the convection. C says to reduce the energy lost due to surrounding by conduction. This is a promising option, but it is talking about conduction. Conduction only happens through solids, and we have vacuum over here. So there is no way heat is lost due to conduction because we have vacuum. Conduction cannot happen through vacuum. So this is again wrong. Option D says to reflect thermal radiation back into the flask. Now this is correct. Radiation is made of infrared rays, which are a form of electromagnetic radiation. They are a form of light. What happens is radiation will try to strike on the walls, but because the walls are shiny, it will be reflected back. Almost all of it will be reflected back. And that's where the silvered walls come into play. Because they're shiny, they will reflect back the radiation, they will reflect back the heat. And that is how they reduce the energy lost due to radiation. So D is correct. Question 20. We have four options. These over here are wave fronts of water waves, and these are the barriers that have small gaps in between them. We have been asked in which of the options will diffraction of water be the lowest. Okay, let's start drawing. So over here, the wavelength of these wavefronts seems like equal to the gap. So we'll have a very high amount of refraction. In the second option, we have a gap which is smaller than the wavelength. So there will actually be no diffraction. There will be no waves across this. The water will reflect back. So option C says we have very small wavelength, but we have a high gap. So there will be diffraction, but it will be very low. It will be something like this. The waves will remain almost parallel. Option D says similar to option A, we have the wavelength which is equal to the gap. So we have maximum diffraction over here again. Now think about in which of these options do we have the least amount of diffraction. In option A, we have the maximum amount. In option D, we have the maximum amount. In option B, we don't have any diffraction, and in option C, we have very low diffraction. So we have the least diffraction in option C. Option B is wrong because we have zero diffraction. C is our answer.